This lecture will be discussing and introducing acid-base chemistry, which will be a little bit of review from the first quarter, but then we'll take it into much more detail in the next few lectures. Right, so the material today we'll cover first, we'll start with some Chapter 4 material, and this is sort of an what we had discussed previously in the first quarter. And then we'll move on to Chapter 18, and this is where we get into more of the details of acid-base chemistry. Right, so just to remind ourselves what some common acids and bases are. Acids like acetic acid, citric acid, ascorbic acid, we see those primarily in foods around the house. These are all weak acids. Some aluminum salts can be acidic as well. Bases, sodium hydroxide, that's a very strong base. Ammonia, that's in cleaners, that's a weak base. And so forth. So what are acids? What are bases? Well, it kind of depends on what your definition of them is, and there's a few that we use. The first one is the Arrhenius acid-base definition. It classifies the substances in terms of what they do when they're in water. Right? An acid, by the Arrhenius definition, is a substance with a hydrogen in it, and it dissociates in water to yield an H plus in solution. Right? And I should mention now, we kind of use these terms interchangeably, H plus or proton, and the hydronium ion, H3O plus. And that's because when a substance, an acid, loses a proton in solution, that proton really doesn't stay separate as an individual proton in water. It will combine with a water molecule to form H3O plus. But you'll see it written both ways, so just note that they mean the same thing. I typically write it as H plus just because it's shorter and it's easier to write. A base, by the Arrhenius definition, is a substance that has an OH in its formula, a hydroxide, and it will dissociate to yield that OH minus in solution. Okay, so this is a pretty simple definition of acid-base based on their behavior in water. Well, when an acid and a base react together, they undergo what's known as neutralization, right? So you'd have H plus OH minus goes to H2O. And that would be the net ionic equation for any acid-base neutralization. So technically, the neutralization of an acid-base will lead to salt and water. Right, the ionic compound, the salt, would be the anion from the acid and the cation from the base. So the classic example, the easiest one, is hydrochloric acid, HCl, and NaOH, right? Sodium hydroxide. They will combine to neutralize to form water, but they also form that salt, sodium chloride. So you have the cation from the base and the anion from the acid. Right, but those will cancel out in the net ionic equation because the chlorine and the sodium are spectator ions. They are, aqueous in solution, and they don't undergo any chemistry. Right, so we can write the molecular equations and remind ourselves what that is. That's written, the molecules like HCl and NaOH are written as they are, undissociated, right? Even though we know in solution they are dissociated, fully dissociated, because they're strong acids and strong bases. Right? The ionic equations write these out as separate species. So the first part of this, we'd have H plus aqueous plus Cl minus aqueous for HCl, and Na plus OH minus aqueous for the base. Right? And then on the other side, right, we still have Na plus and Cl minus, but we have H2O liquid now. And for the net ionic equation, you would just cancel what's the same on both sides, and that's the Na plus and Cl minuses. They cancel, and what we get is the net ionic equation, which is H plus OH minus goes to H2O. Right. Strong acids and strong bases. This is sort of, again, review of what we talked about in the first quarter of general chemistry. But that definition of strong acid and strong base means they're completely ionized or dissociated in solution, i.e. they're strong electrolytes. And the strong acids that we need to remember in this class are the halogens, except for fluorine when they're combined with hydrogen. So hydrochloric acid, hydrobromic acid, hydroiodic acid. And the other ones that don't fit into that category would be nitric acid, HNO3, sulfuric acid, H2SO4, and perchloric acid, HClO4. Okay, but this perchloric acid, we don't see that as much. Definitely the top 5 are probably, you run into those more often. All other acids you can assume to be weak. Right. So some examples of weak acids that you see more often, especially in this class, HF, H3PO4, phosphoric acid, and acetic acid. And in fact, anytime you see this COOH, that's going to be an organic acid. It's a carboxylic acid group, and you can assume those are always weak acids. Strong bases, these are kind of easy to identify because they're a metal of some sort with an OH on them, right? So they're ionic compounds. The OH group is the anion that will dissociate in water completely. So yeah, any strong base is going to have an OH in it. There are weak bases too, and they contain nitrogens usually. So ammonia is the classic example, but you can have, carbon compounds that have an NH2 or an NH3 in them, and those are considered bases as well. So a review question, which of these are strong acids? Okay, so if we go through this, right, what are the strong acids? They are the halogens, except for HF, and sulfuric acid and nitric acid. Okay. So do we have any of those? Yes, we have HCl, HBr, hydrobromic acid, and we have sulfuric acid. Okay. Phosphoric acid, acetic acid, and HF are all weak. Right, so this would be 1, 3, and 4. What are the major species present in an aqueous solution of 1 molar HCl? Well, if we put HCl in solution, what happens? It completely dissociates, right? It's a strong acid. So we get H plus ions and Cl minus ions in solution. Right, and remember, H plus is the same as H3O plus when it's in solution. Okay, so what do we have here? The major species. Well, do we have any HCl? No, it's completely dissociated. Okay, and it's completely dissociated into Cl minus and H3O plus. And the other species that's going to be present is the bulk water. So this would be choice 2, 3, and 4 would be choice B. Another thing we talk about in chapter 4 that we talked about last quarter was titration. Okay, and what is a titration? It's a volumetric method to determine the concentration of an unknown substance. In this class, most commonly an acid or a base, by reacting it with a standard solution. Standard solution is known as the titrant. That's when you know the concentration of. When you reach what's known as an equivalence point, that's when you have enough standard solution added to completely react with the unknown substance. And hopefully your end point in your titration is basically the same as the equivalence point. That's how you know it's done. Right, so if you're titrating your sulfuric acid with NaOH, sodium hydroxide, right, at a certain point, your indicator solution you have in there will turn pink when you have added just the right amount of base to counteract that acid. Right, so if our H2SO4s are unknown, that's the NaOH then would be our titrant. That's what's in the burette. Right, the endpoint is shown when that indicator changes. Stoichiometry, how do we deal with this? Well, the roadmap is shown here, right? You have basically it's like any chemical problem-solving problem. You have enough information to determine the number of moles of one thing. In this case, that would be our standard. Then you convert the moles of standard into moles of your unknown, which is the acid, and then you know the volume of the unknown, so you can get the concentration of it. So let's try a quick review using a titration. What is the concentration of sulfuric acid at 15 milliliters? It reacts with 18.45 milliliters of a 0.0973 molar NaOH solution. Okay, so first part, we need to determine our moles of our standard. In this case, that's our NaOH. So we had 18.45 milliliters is our volume, and so we can convert that into liters. That's 1,000 divided by 1,000. And that's because our concentration units are in moles per liter, so we need that to cancel. Right, so then our number of moles is just going to be our concentration times our volume. So our concentration was 0.0973 moles per liter. We multiply that by our volume. And what do we get? We get 0.001795 moles of NaOH. Right, so that's our first step. Second step, convert to moles of our acid. And how do we do that? We do that using the ratio in a balanced chemical equation. So that's really what I should have done to start this off with. But what do we have our reaction? We have sulfuric acid, which is H2SO4, and we're adding NaOH. So what are we producing? We're producing a salt, which is sodium sulfate, and water. Right, this is an acid-base neutralization, so that's what we produce, as salt and water. Okay, to make the stoichiometry correct, we're going to need to add a 2 in front of sodium hydroxide to balance the 2 sodiums that need to balance the charge of sulfate. And we'd also need to add a 2 in front of water. Okay, so that's our balanced chemical equation. So the mole ratio you see is 2:1 sodium hydroxide to sulfuric acid. So to convert from moles of NaOH, we're going to need to divide by 2. So we have 0.001795 moles of NaOH, and then that ratio is 1 mole of H2SO4 for 2 moles of NaOH. And again, that's from the balanced chemical equation. So that's 0.008975.925. Wow. Don't need to keep that many significant figures in, but I'll just do that until the last part. And that is our acid. Right, it's easy to, try to do this step in your head, but when you do that, it's kind of easy to sometimes multiply by 2 instead of divide by 2. So I find, actually keeping these units explicitly written out so you know that they cancel really helps. And so the third part of a titration is calculating the concentration of your unknown. So in this case, our H2SO4, right? We have the number of moles. That's a 0. Whoop. 0. 0, 0, 0, 8975. 925. That's moles divided by our volume, and we're given 15 milliliters, but we want that in liters, so that should be 0.015 liters, right, which will be approximately 0.06 molar. Okay. So if you're given titration, just remember you need to know the balanced chemical equation, and it helps to break it down into like 3 separate steps, at least for me, and not try to do it. I know in the problem sets they when they show you the answer, they kind of do it all at once in one single step, but I think it's easier to break it down into these 3 steps. Okay, so that was our review of chapter 4. Moving on to chapter 18, and this is where we get into more details of acid-base chemistry. So up until now, we've only really discussed strong acids and strong bases, but there are weak acids and weak bases as well, and they only dissociate partly in water. Okay, so that's what makes them weak as opposed to strong. Right, and as we've kind of covered equilibrium, right? That's what these weak acids and weak bases would be considered an equilibrium system. So we're going to use the double-headed arrow to indicate that in these chemical equations. So for our acid, all right, if we have CH3COOH, right, that's a weak acid. It'll dissociate in water, but not to a very large extent. So we show that equilibrium with a double-headed arrow. And a weak base, likewise NH3, it will grab a proton from water and create NH4+, and that's what makes that the water that gave up that proton becomes OH-, and so that's why it's considered a base. Okay. So the net ionic equation for these is the same as it would be for a strong acid or a strong base, right? And that's shown here as well. Okay, so if we compare these graphically, strong acid, just generic strong acid, we can write as HA, right? Before you put it in water, you have, a certain number of moles of HA. After it goes in water, it dissociates completely. You'd have the same number of moles of hydronium ion and the A minus, what's known as the conjugate base, but we'll talk about that in a second. All right, again, strong acids, and we talked about this in chapter 4, but here's showing how they ionize in water. One thing I will mention, point out, sulfuric acid, we have 2 protons on it, so it's diprotic, and meaning you can lose 1 proton, and then you would actually lose another proton as well. So there's 2 steps to sulfuric acid. Okay, what about weak acids? Well, remember they only partially ionize in water. So HNO3, nitric acid, is a strong acid, but here we have HNO2, nitrous acid, and this is actually a weak acid, right? So it dissociates, but not completely. So we show that with that equilibrium arrow. If we had a certain number of moles of nitrous acid or any weak acid, right, before we put it into water, right, we put it in water and it will dissociate, but only partially. Right, you'll notice that there's a very small amount of H3O plus and A minus, which would be NO2 minus in this case. Right, the majority stays completely associated together in a molecular form. So that's what makes it, we consider it weak. So we can show this equilibrium between acid on the left and the ions on the right. And from our equilibrium discussion, we know we can write an equilibrium constant for this, right? And that's products over the reactant. So we have our dissociated form of the molecule and hydronium ion on top. Those are our products, divided by our reactants, which would be the weak acid and water. Okay. We can consider, though, H2O concentration to be constant because it's in these solutions are in water, bulk water, and that they're just water molecules are in such great excess that the amount that comes that we lose for making H3O plus, we can kind of consider that to be negligible. So H2O concentration is constant, so we can get rid of it from this discussion in terms of our equilibrium. And that becomes our Ka. So that's the equilibrium constant for an acid in solution, dissociating in solution. And it simplifies a little bit, right? So we have the dissociated form concentration of that plus the hydronium ion concentration divided by the concentration of your weak acid. So strong acids, the Ka value for strong acids would be very large, so much, much greater than 1. Weak acids, the Ka value is less than 1, and oftentimes it's a very small number, like 10 to the minus 3 or 10 to the minus 4. And here are some Ka values for some weak acids, and their relative strengths are shown here with the weaker ones shown at the bottom and the stronger acids at the top. But again, these are all considered weak acids. So we have, things like chlorous acid, HClO2, nitrous acid, HNO2, hydrofluoric acid, HF. in some of the organic acids like formic or acetic acid are shown here. And again, here's that COOH when it's written like this. What it looks like is here. This is a carboxylic acid. And if you take organic chemistry or biochemistry, you see lots of these. And you'll notice the range of these Ka values, right? Something up here like chlorous acid is 1.1 times 10 to the minus 2. All the way down here, we have, for cyanide, hydrocyanic acid, we have times 10 to the minus 10th. So that's very, very weak. Strong bases, again, we've mentioned these in chapter 4. This just shows how they dissociate in water, their dissociation reactions. Okay, but basically you have group 1 and 2 metals with hydroxides on them. Weak bases, these are nitrogen-containing compounds for the most part. You can have ammonia, that's very simple. It's just NH3. But you can have the NH2 groups that are in organic molecules too. So molecules that are made out of carbon will have an NH2 group on them. That is a weak acid. So we have a base NH3 group. When that's added to water, you're going to make a small amount of NH4 plus, which would be considered its conjugate acid. And we'll talk about conjugate acid base pairs later, but we'll just throw that term out here now as well, get used to it. And that water, again, the water that gave up a proton becomes an OH minus, and that's where we get why these are considered bases. Much like an acid that you can write a dissociation constant for, a Ka, we can write a dissociation constant for a weak base as Kb. And those values, again, for weak bases are going to be less than 1, oftentimes very, very small. Comparing acids and bases, strengths of acid and bases. So on this side we have their acids written. And on this side is what their conjugate bases are. So their conjugate base of an acid is what that molecule looks like after it has given up a proton. Okay, so H2SO4, conjugate base would be HSO4. HNO3, conjugate base would be NO3 minus, and so forth. Okay, so the stronger the acid is, the weaker the base, the conjugate base would be. Right. So very strong acids have very weak base conjugate acids. And the opposite is true. If you have a very strong base, its conjugate acid would be very weak. Strong acids all have the same strength in water because they're all completely dissociated. So it's hard to compare, strengths of strong acids. Okay. Let's try a practice question. Classify each of the following compounds as either a strong acid, strong base, or weak base. Okay, so let's look at A. Right, so A, that would be a strong base. We have a group 1 metal combined with an OH. So when that dissociates completely and we get OH minuses. CH3 to COOH. And remember that COOH, that's a telltale sign that this is a weak acid. It's a carboxylic acid. So here we have a weak acid. H2SeO4. This one is it's kind of a trick question. I keep forgetting to take this out of here, but it's like H2SO4, and it's actually a strong acid. I know that slide said, you know, these are the 6 strong acids. Everything else you can consider weak. And then we have this problem here that gives you this H2SeO4, selenium acid. And it says it's strong. So, you know, on an exam, I'm not going to give you this one, right, and ask you if it's weak or strong, because the only strong acids you can consider are those 6 that were shown on the slide before. And then finally, we have this group, CH3-2CHNH2. So this is an organic molecule with a amine group on it, right? Remember, those amines are weak bases. Okay, so the second part of this question, write a Ka expression for any weak acid. So we have a weak acid here. And what would it look like in water? Well, we'd have CH3-2, CHCOOH, and when it dissociates, sorry, that's an H. When it dissociates, we get CH3-2, CHCOO minus, plus H3O plus. Right, so our Ka expression would be the concentration of our conjugate base, CH3 CHCOO minus, times our hydronium ion concentration, divided by our fully intact weak acid. So CH3-2 CHCOOH. Okay. So hopefully that should be, you know, fairly straightforward, very similar to what we've been doing with equilibrium. Okay, second question. Estimate the Ka values for the acids shown below. Oh, excuse me, examine, not estimate. You won't have to estimate. You won't have to memorize Ka values. If you need them on an exam, you will be given them. Okay. So we have a list of 4 acids here and the Ka values for each. Right, so we're considering 0.1 molar solutions of each, right? So they all have the same concentrations. We have to arrange these solutions in order of increasing H3O concentration. So in other words, in terms of increasing acid strength, right? Because the stronger the acid is, the more H3O plus you're going to produce, the more it will dissociate, and the higher the Ka value will be. So Ka values increase with increasing acid strength. So I guess what we need to do is determine which one of these is the weakest, and that will have the lowest Ka value. So for that, definitely look at the exponents first. So phenol is 10 to the minus 10. So that's the lowest. So we'll just put that, let's rank that as, you know, if we go increasing numbers, we'll just rank that as, give that a value of 1. The next lowest would be hypobromous acid at 10 to the minus 9th. Then acetic acid, 10 to the minus 5th, and formic acid is 10 to the minus 4th. So it's the strongest. Right, so weakest to strongest, we would go phenol, followed by hyperbromous acid, then acetic acid, and finally formic acid. So that would be choice C. Okay, so a question like this should be hopefully very easy. You're just ranking in terms of Ka values. The lower the Ka is, weaker the acid. The higher the Ka is, the stronger. Final practice question. What are the major species present in an aqueous solution of 1 molar acetic acid? Right, so let's write our reaction here. What happens in water with acetic acid? Well, we get it to dissociate, but it's only a weak acid, so it doesn't dissociate fully. It only dissociates to a very small extent, actually. So the major species that would be present would be the undissociated form of the acetic acid. You'd still have quite a bit of water as well. Would you have a lot of H3O plus? Well, no, because this reaction doesn't go forward very much. And likewise, you wouldn't have very much of that conjugate base either. And then OH minus, that would be a very, very minor species as well, because this is in bulk water and a weak acid solution. So we wouldn't have much of that either. So the major species here in any weak acid would be just that undissociated form of the weak acid and water. And if we write our expression, this is, maybe you don't really need to know this right now, but this is kind of where we will be going with this in the next lectures. You can write your expression for Ka for this. All right, so that'd be our expression for Ka. Right, and we know the Ka value for this. You can look that up. It's 1.8 times 10 to the minus 5. And we were given a concentration of our undissociated form. We don't know how much this dissociates, right? But we can use the variable x for these concentrations. So that would become x times x on the top divided by, and we can just estimate this as what it started with, 1 molar. So we have x squared over 1 equals 1.8 times 10 to the 5th. So you can solve for x for this, and you get something like 0.0042 molar. So that's, basically that would be the concentration of the hydronium ion and the conjugate base of acetic acid in solution. And you can see that that's a very low amount compared to 1 molar, right? So that's why we consider these very minor. Okay, just briefly mention a little bit of section 2 material. This is where we'll be going with next time. And that's the what's known as the autoionization of water and the pH scale. Right, so the autoionization of water, it turns out it can actually act as both a base and an acid. Right, so the base, how it acts as a base is it can take a proton from another water molecule, and the water molecule it takes one from is acting like an acid, right? It's giving up an acid. So what you're producing when that happens is a H3O plus cation and OH minus anion. And we can write our equilibrium expression for this, that's very simple. It'd just be our products over reactants. Okay. And we know that the H2O minus, or excuse me, H2O concentration isn't really changing, right? It's in bulk water, so we can kind of throw that out of our expression. and then that simplifies to H3O plus times OH minus, and this is known as the Kw. And it turns out that there's a value for this. It's 1 times 10 to the minus 14th. Okay. In the absence of any other acids or bases at room temperature, essentially 298 Kelvin, the concentration of H3O plus equals the concentration of OH minus, right? So if you know these equal the same, so that'd be like x squared. You would take the square root of both sides, and what you'd get is 1 times 10 to the minus 7. So the concentration for a neutral solution of water with no acids or bases added, the concentration of H3O plus would be 1 times 10 to the minus 7th. And that's kind of a prelude to what we'll be talking about next time, how you actually calculate a pH value.